The purpose of this lab is to observe the changing position of an object that falls from rest and compare this observation with two models that predict the position of the object. The object I observed for this lab was a sponge. I analyzed its movement and position using Tracker and created two computational models of its position using GlowScript. The computational models applied the velocity update version of Newton's second law as well as the position update formula to predict the future position of the sponge. The fundamental principle applied in this lab is Newton's second law. Newton's second law relates the net interaction between system and surroundings to the observed motion of the system. To elaborate on this, Newton's second law states that an object that has non-zero net interactions will be accelerating, so it experiences non-constant velocity motion. The velocity update formula, which I used in creating both computational models of the sponge's position, can be derived from Newton's second law. After writing in terms of final and initial momentum, I divided both sides of this equation by mass. Then, adding initial velocity to both sides results in the velocity update formula. The procedure for this lab was to record a video of an object falling from rest and then analyze the video in Tracker. From there, the procedure was to construct a computational model to predict and display the object's position that only considers gravity, and another model that considers both gravity and the drag force. Here is a clip of a sponge falling that I analyzed in Tracker. The sponge is the system in the video and everything else are the surroundings. I chose to orient the positive x-axis to the right and the positive y-axis is up. For each frame of the video, which represents one time interval, I placed a pointer on the center of mass of the sponge. Doing this generated a graph of the sponge's position at each time interval. After tracing each change in position, I let the sponge's initial velocity be 0 since it is falling from rest. Here is a screenshot of the code for the first computational model I created. First, I changed the object's mass to match that of the sponge, and I then updated the velocity and position equations to be the velocity and position update formulas. These are velocity equals velocity plus net force divided by mass times delta t, and position equals position plus velocity times delta t. Then I changed the net force to be the weight force of the sponge, since I am assuming the sponge is only affected by gravity for this model. I calculated the weight force by setting a new variable w equal to the mass of the ball times acceleration due to gravity times the unit vector for the positive y-axis. Then I changed the time step delta t to match the time steps of the recorded data from Tracker. Lastly, I updated the initial position to match the position from the Tracker data. Here I am assuming the sponge is accelerating throughout the video. This program generated a chart of where the object's position should be at increasing times when it has an initial velocity of 0 and is accelerating due to gravity. Here is a screenshot of the code for the second computational model I created. I made the same adjustments as I did for the first model, except this time I also considered a drag force to be acting on the falling object. To add this to the net force, I created three new variables: speed, v hat, and fd. These represent the magnitude and direction of the velocity vector and drag force. The drag force is the product of the square of speed, v hat, and the drag constant b. I found b by plugging in values until the final position predicted by the model matched the final position extracted from Tracker. Here is a graph comparing the data extracted from the observed and model position versus time graphs. You can see that the line representing the gravity model diverges completely from the observed position, and the gravity drag model is more accurate. The observed position also diverges from the gravity drag model, but at a much smaller scale. Sources of error that could explain the inconsistency between the gravity drag model and observed positions such are inaccuracies in tracking position in Tracker and other potential outside forces acting on the sponge. The key difference between the gravity and gravity drag model is that in the former, the drag force is not considered. This makes the gravity drag model an improvement from the gravity model, as it can more accurately predict the position of the sponge as it falls. To conclude this lab, I'll talk about which model reaches terminal velocity and how initial velocity affects terminal velocity. The model that only considers gravity cannot reach a terminal velocity since drag force is a component of terminal velocity and it is excluded from this model. The gravity drag model, on the other hand, does reach terminal velocity. At around 0.4 seconds into the sponge's falling motion, its velocity time graph transitions into a straight line. Straight lines are linear and have a constant slope, which means that at this time the velocity becomes constant. According to Newton's second law, objects moving with a constant motion have a zero net force. Since the two forces acting on the object as it falls are gravity and drag force, they must be equal in magnitude and opposite in direction when it reaches terminal velocity. This is a screenshot of the velocity time graph of the sponge where its initial velocity is 0, -1, 0 meters per second to represent the object being thrown. As you can see from the graph, the terminal velocity is not affected by initial velocity of the object. The graph shows that the magnitude of terminal velocity will be the same, and the only thing affected by a different initial velocity is how quickly terminal velocity is reached. It's faster in the case where the object is thrown down. And that is all I have. Thank you.